In this video, we're going to look at how, given a matrix, you can test whether or not it's diagonalizable and calculate what the diagonalization of the matrix is. In the last video, we saw a walkthrough of an example of diagonalizing a matrix. So as a recap, remember that diagonalizing a matrix refers to finding a pair of matrices, one of which is invertible, the other of which is diagonal, so that you can write the matrix you're interested in as the product of the invertible matrix times the diagonal times the inverse of the invertible matrix. And one of the advantages for working with this matrix is it gave us some idea of our structure of A, and in particular, the matrices P and D were telling us stuff about the eigenspaces. Other bonuses, we could write A to the K as a product of P D to the K times P inverse. So we got some bonus information out of knowing that we had a diagonalization of a matrix A. So our 4 steps for calculating this diagonalization include, we start by finding the eigenvalues. So we'll do that by, at least in this course, by looking at the characteristic polynomial. So we'll calculate our determinant of A minus lambda I to the n, or in, and find the roots in terms of lambda. Once we have our eigenvalues, we'll find n linearly independent eigenvectors, and so this is exactly the condition for such a diagonalization to exist. So if we're able to find essentially enough vectors in our space to construct an eigenbasis, we'll be able to use it to construct a diagonalization. Once we have our n linearly independent eigenvectors, we're able to compute both our matrices P, where our columns are eigenvectors, and our diagonal entries of our matrix D, dii, along that diagonal, will be our ith eigenvector, or eigenvalue, sorry. So let's actually look at this matrix here and actually practice all of these steps, checking that we both understand what computing a diagonalization of a matrix means and that we understand all 4 steps involved. All right, let's actually go about finding our eigenvalues. So as a reminder, to find the eigenvalues of a matrix, if we're doing it by hand, we're going to compute the characteristic polynomial, which is the determinant of our matrix A minus lambda times the identity matrix. And we'll look for our roots, setting this characteristic polynomial equal to 0. So our A minus lambda I3 is going to be 1 minus lambda, 3, 3, negative 3, negative 5 minus lambda, negative 3, 3, 3, and 1 minus lambda. So as a reminder, to compute the determinant of a 3 by 3 matrix, we're going to expand along the first row in this case. So alpha equals, our determinant is 1 minus lambda times our determinant of this 2 by 2 submatrix. Minus negative 3. So in this case, I'm going to just add 9. Minus 3 times our determinant of the submatrix we obtained by deleting our center column and our top row. So we get 3 minus negative 3 times 1 minus lambda, minus, looks like another negative 9. And then we add 3 times our determinant of this submatrix, so plus 3, negative 9, minus, that's going to become 5 plus lambda, times 3. So this is our characteristic polynomial that we're going to look for roots of. After doing a little bit of simplification, let's look at what this turns into. So keeping most of the messy algebra off screen, what this would have simplified to after expanding out all of these terms in our products is lambda cubed plus 3 lambda squared minus 4. I can actually factor this to get lambda minus 1 times lambda plus 2 lambda plus 2. So from this, setting this equal to 0, we can see that our 3 eigenvalues are going to be lambda is equal to 1, and lambda is equal to -2, with the term we use for having multiple eigenvalues of the same sizes, -2 has multiplicity 2. And since there are two copies of it, and lambda equals 1 has multiplicity 1. So the number of copies of our eigenvalues is fine. Having repeated eigenvalues, by the way, is not going to prove that we don't have a diagonalization of the matrix. We're still, given multiple eigenvalues, or repeated eigenvalues, we'll often still be able to compute a linearly independent spanning set for our eigenbasis. So now that we have our three eigenvalues, including -2 with multiplicity 2, we're going to use this to calculate our eigenvectors. So as a reminder, to calculate an eigenvector, we look at all of our distinct eigenvalues and form the matrices A minus, in this case one of our distinct eigenvalues is 1, times the identity matrix. So for this, it'll be the matrix 0, 3, 3, -3, -6, -3, and 3, 3, 0. So to calculate our eigenvectors from this matrix, we row reduce to the reduced echelon form, which in this case is 1, 0, -1, 0, 1, 1, and 0, 0, 0. So our eigenvector corresponding to eigenvalue number 1 is any vector of the form v lambda, where looking at this we have one free variable, which we'll call t, and we see that our vectors will be of the form t, -t, t for any t inside R. So in particular, we can choose the eigenvector 1, -1, 1. For our second distinct eigenvalue, -2, we'll form the matrix A minus -2, which will be 3, 3, 3, -3, -3, -3, and +3, +3, +3. So you note that this is actually row equivalent to a matrix with two free variables. So our dimension 2 eigenvector set corresponding to -2 is spanned by the vectors, the vector t, -t and t, 0, and -s, 0, s. So our free variables were our second and our third variables here, so our y and our z. So our x here could be any value that satisfies either of these relations. So we note that even though we only have two distinct eigenvalues here, we actually have a dimension 2 eigenspace corresponding to -2. So with this, we're able to find two possible eigenvectors. So we'll call this maybe v lambda 1. We'll call v lambda 2 -1, 1, 0. And v lambda 3 will set to be -1, 0, 1. So these three eigenvectors that we have, a quick check that we could do is forming, to make sure that all three of these really are linearly independent, is we could form the matrix with columns v lambda 1, v lambda 2, and v lambda 3, which we'll actually use this matrix again. This is going to be our P that we're going to form in just a little bit, and calculate this determinant. So just check that the determinant of this matrix P is non-zero. All right, now that we have our three linearly independent eigenvectors from above, we can calculate P by just placing each of those eigenvectors as a column in our new matrix. So this 1, -1, 1, -1, 1, 0, and -1, 0, 1, this is going to be our matrix that we'll use to construct our diagonalization. And note that having these v lambda i's independent is necessary to have P inverse, necessary for P inverse to exist. And I'm going to use software to calculate P inverse here. So our P inverse is going to be 1, I believe it's 1, negative 1, 1, 1, 2, 1, negative 1, negative 1, 0. I'll do a quick check and fix this if that's off, but I believe that's our inverse. Just kidding, it's close. So it's 1, 1, 1, 1, 2, 1, and negative 1, negative 1, 0. So this inverse, you guys could compute this by hand through a variety of techniques we've done in class. But again, the fact that this inverse exists is guaranteed by the fact that these set of eigenvectors that we formed our columns with were linearly independent. So this is our P and our P inverse that we're going to use in our step 4, or I guess technically our bonus step where we check that our multiplication works. So now that we have our P and our P inverse, recall that to create our D, we're going to set up a diagonal matrix where our diagonal entries are the ordered eigenvectors we used before. So recall, like since our first column here of P corresponded to eigenvector 1, we'll make sure that 1 is our very first entry. Our second and our third rows of this matrix are both, our second and our third rows are both corresponding to eigenvector negative 2. So we're okay regardless of which order we put these in our matrix, but we need to make sure that our second and our third diagonal entries correspond to eigenvalues negative 2 and eigenvectors in the second and the third column of P. And so this is our diagonal matrix that our decomposition depends on. And note, a good check to do at this point using software if you have it available is making sure that your original matrix A does correspond to the product of this P, D, and P inverse that we've constructed. So our P, again, this 1, negative 1, negative 1, negative 1, 1, 0, 1, 0, 1, times this diagonal matrix of our eigenvalues, times our inverse of P. This should be that original matrix that we began with on the previous slides. So I'll leave this for you guys to verify, and we'll actually do another example using MATLAB code, but in Octave in just a moment. So one nice property that comes out of the construction we used is a theorem that gives us, again, a sufficient condition, but not necessary for diagonalizability. So a sufficient condition is if you calculate, if your matrix has as a characteristic polynomial of the form a minus lambda I n, where each of your eigenvalues, so this will factor into lambda minus lambda 1, lambda minus lambda 2, up to lambda minus lambda n, if this set of lambdas, lambda 1, lambda 2, through lambda n, has n distinct values, since each eigenvalue has at least one eigenvector, and in this case at most one eigenvector, this will guarantee that we're going to have n linearly independent eigenvectors, one for each lambda I. So I'm going to omit this proof here, but this will be one, again, sufficient but not necessary condition. Note that in our previous example, we had, so if our eigenvalues are something like 1, 3, and 5, so our set of lambdas was something like that, we would have, A would have an eigenspace, or A's basis would, the basis of the domain of A, eigenspace exists, and A is diagonalizable. But we've seen an example where our set of eigenvectors, I'm using big lambda here to capture them, was positive 1, negative 2, and negative 2, where we actually were able to construct a nice diagonalization of A for this. So this is, again, it's sufficient but not necessary. So let's look at one more matrix to see how we could how we could identify whether or not, let's just run through maybe in software, how we would go about constructing a diagonalization of a matrix. So let's look at an example without distinct eigenvalues that still works. So one of the nice bonus things that we're able to do is, given a diagonal matrix, or given an upper or lower triangular matrix, we can do a quick check by looking at our entries along the diagonal. One of the nice properties of a matrix that's upper or lower triangular is that we can identify immediately what the determinant is, so the product of all the entries on the diagonal, and the characteristic polynomial, which is going to have roots given by each of our entries here. So for this matrix, not doing it in software, I can do a quick check on what my determinant of A minus lambda I is without doing any sort of computational heavy lifting. I know it's going to look like lambda minus 5 squared, since there's two of those, and lambda plus 3 squared, since there's two negative 3's. So our set of eigen values for this matrix are 5 with multiplicity 2 and negative 3 with multiplicity 2. With these guys in hand, we could actually go through and quickly compute our eigenspaces using the matrix A minus, so row reducing the matrix A minus 5 lambda and A plus 3 I4. Looking at those, let's actually see how we can do this in MATLAB. So I'm going to pause this and hop over to MATLAB with copy of A. So in this instance, I have Octave running instead of MATLAB, but the commands are going to be identical. So for A, I've entered the matrix that we were looking at on our slides, so we can see our 4x4 matrix. And as a reminder, the command in MATLAB to get the identity matrix is the word I. So our I4 is the diagonal matrix with ones along the diagonal. So in our previous, just by hand, we had computed our characteristic polynomial. There's actually a command in MATLAB called poly that will pull this as well. So one of the downsides to using the characteristic polynomial is, what this is telling you is this is the polynomial lambda to the 4th minus 4 lambda cubed minus 26 lambda squared plus 60 lambda plus 225. Our actual characteristic polynomial is a little easier to see in the factored form that I have on a slide, but we could use this to actually compute what our characteristic polynomial is. Alternately, a nicer way to actually get to the eigenvalues directly, since MATLAB isn't going to be computing your eigenvalues using the characteristic polynomial, what MATLAB can do is we can make our set of lambda be the eigenvalues of A. So that list of lambda is now our two eigenvalues, negative 3 and negative 3, and our two eigenvalues, 5 and 5. So the command eig of A will actually construct your eigenvalues. Neatly enough, you can actually construct a little more than that. So the lambda, instead of eig of A computing simply the eigenvalues, you can actually have it compute your entire eigensystem. But unfortunately, it's a little hard sometimes to see, just looking at this, a nice representation of what your eigenvectors are going to be. So going back to our original A. With this A in hand, knowing that we've got eigenvalues 5 and negative 3, we can actually take A minus 5 times the identity matrix. So this is our matrix where we subtracted 5 from all of the entries along the diagonal, and we can row reduce this matrix. So this gives us a basis for our eigenvectors of A. So looking here, we can see that our two free variables are variables 3 and 4, so we have a dimension 2 set of eigenvectors. So I'll pull these over and write them on the slides in just a minute, but in terms of checking whether or not a matrix is diagonalizable, it's sufficient for us to find out, for both of our possible eigenvalues in this case, if both of them are dimension 2, so which they are, we've got two free variables S and T that we can choose to be anything we want. With this, it's going to be, we actually know since both of our spaces are dimension 2, our eigenvectors must have 4 linearly independent entries. So I'll put those back on the slides, but in terms of checking whether or not our matrix is diagonalizable, we're actually done. So you note I've added to my slides for eigenvalue positive 5, I picked 2 eigenvectors in our basis. And for eigenvalue negative 3, I've picked 2 different vectors. So these are drawn directly from that calculation of our reduced row echelon form of A minus 5 like times the identity matrix and A plus 3. So this is where we got our our dimension 2 bases for each of our sub-eigenspace. From this, we can actually see that our matrix P that we'd be interested in, again, keeping my diagonal entries in this same order, a matrix P that would work would be negative 8, 4, 1, 0, negative 16, 4, 0, 1, 0, 0, 1, 0, and 0, 0, 0, 1. So again, this is for a diagonal matrix D with entries 5, 5, negative 3, and zeros off the diagonal. So I'll leave it to you guys to check. Actually, I'll swap back to software and just do a quick check that the P that we see here really does give us the same A that we started with. So I've already input into Octave our original A, and I've put in this new P that we calculated by hand, which is not very pretty, but we'll be able to check it in just a second that we get what we want. And our diagonal matrix, again, the order is very important when you're constructing these. Make sure that your eigen values are in the order that you put the columns inside this matrix. So let's just do a quick check if P times D times P inverse really is the A we started with, and we see it is. So this was a nice construction in that we can do this by hand, although the hard part is often going to be computing this inverse, which is, you can do it and you guys know how, but I'm happy with us using software to check a lot of these things. When we come back next week, we'll be trying a lot of new topics. So we'll be moving from matrix diagonalization and eigenvalues to how we can use these matrix diagonal constructions to get an approximate solution to matrix equations. We're also going to look at inner products in length, which is going to be a way of measuring angles or distance between vectors, and look at what it means to be orthogonal. So this orthogonal is right-handedness or at right angles to one another. So we'll see what that means formally and how we're going to define that using inner products. So I'll see you guys next time, and take care.